안녕하십니까. 키노트 스피치 저장을 맡게 된 연세대학교 용인 세브란스 병원 최동원 교수입니다. 제가 마침 또 이 대한의료정보학회 추계학술대회 조직위원장을 맡아가지고 저희 용인 세브란스 병원에서 이걸 유치하게 돼서 굉장히 영광스럽게 생각합니다. 이번 키노트 스피치를 하실 분은 레오 앤소니 셀리라는 분이시고 외국 분이시기 때문에 제가 이분에 대해서 간략히 영어로 설명을 드리겠습니다. Let me introduce the keynote speech. Leo is a clinical research director and principal research scientist at the MIT Laboratory for Computational Physiology. And he's right now practice ICU physician at the Beth Israel Deaconess Medical Center. He brings together clinicians and data scientists to support research using data routinely collected in the process of the care. His group built and maintains the publicly available medical information MIMIC database and the Philips MIT eICU Collaborate Research Database with more than 20,000 users from around the world. Leo is also involved in education and the editor of textbook and also editor of PLOS Digital Health. And he is right now on screen. Dr. Leo, can you hear me?
Hello. Yes.
Oh, okay. So, are you ready for your talk?
Yes, I am.
Okay. Please.
Okay. 안녕하세요. The title of my talk today is Better Than Humans, Building AI That Is Less Prejudiced, More Fair. I'm speaking from Cambridge, Massachusetts. I wish I could be there today, but perhaps next year. Before I begin, I wanted to acknowledge that we get research funding from the National Institute of Health, as well as several industry partners. I represent MIT Critical Data. It's a global consortium consisting of healthcare providers, computer scientists, engineers, and social scientists whose mission is to put data and learning at the front and center of healthcare. We build communities across disciplines to extract knowledge from data that is routinely collected in the process of care in order to understand health and disease better and in the local context. Our flagship project is called MIMIC, the Medical Information Mart for Intensive Care. It was the first resource of this kind. It is a repository of data that is obtained from all patients admitted to the intensive care units of Beth Israel Deaconess Medical Center, where I work in. And we have de-identified the data and share it with the research community. It consists of all the vital sign recordings, the laboratory data, the waveforms that are captured at the bedside monitors, and pretty soon the waveforms also in the ventilators, the notes that are written by the doctors, the nurses, and the different healthcare professionals working in the intensive care unit, and also the medical images. So the most recent iteration of the data set is called MIMIC 4. And for the first time, it contains medical images with 350,000 chest x-rays that are linked with the electronic health record. And next year, we will be including 150,000 echocardiograms, which is 50 terabytes in size. In 2016, our laboratory also partnered with Philips, and we were able to convince them to share data coming from 200 hospitals across the United States with the research community. This is called the eICU Collaborative Research Database. It is also de-identified, And the way to apply for access to these databases is to submit an online certificate of training in human subject research and sign a data user agreement. As part of the data use agreement, the applicant promises to share the codes and queries that they put together in the context of a research project. And these codes and queries are also shared with the research community as code repositories. So we have a Mimic code repository, and we also have an EICU code repository. This allows other groups to replicate any analysis, any modeling that is submitted for publication. And it also allows different groups to build up on each other's research without starting from scratch. And this, I think, is our biggest contribution to the research community. We make it much more collaborative, we make it easier, and we lower the barrier for anyone to use these databases to address a clinical question. We are also invested in training the next generation of clinicians, computer scientists, and engineers. In 2016, we published our first textbook called Secondary Analysis of Electronic Health Records. And in the true spirit of MIT, we decided to make the digital copy of the book completely free of cost. Since 2016, the book has been downloaded more than 1 million times, and it has been translated into Mandarin, Spanish, Korean, and Portuguese. We teach a course at MIT. A fall course is called Collaborative Data Science for Healthcare. During the course, the students work with nurses and doctors from Boston area universities and work on a project that is eventually published in a peer-reviewed journal. Projects that arise from the course have been published in journals such as Nature Digital Medicine and Lancet Digital Health. We created an online version of the course that is now available at MIT Open Learning Library. We also wrote another textbook called Global Health Informatics, and this accompanies another course at MIT during springtime. And just like the first course, we have made an online course that is available for every learner around the globe. The course is called Global Health Informatics to Improve Quality of Care, and it can be accessed through the MIT Open Learning Library. Last August, we published our third textbook, Leveraging Data Science for Global Health. The problems that we face now are all interconnected, from the pandemic to global warming to structural inequities. We highlight in this book that for data science to be optimized and valuable, we have to have a multidisciplinary approach to data science. Data and learning should also be at the front and center of global health. Every patient encounter is an opportunity that we could learn from, and we contend that every healthcare provider, every doctor, every nurse, every pharmacist should be a contributor and a custodian of the medical knowledge system and not just a passive recipient. The best part of our initiative is traveling around the world and organizing what we call datathons. Datathons are short for data hackathons. During these events, we partner clinicians with computer scientists and engineers, and over a span of 2 to 3 days, they get some experience in working with real world data. We have been to Seoul 2 years now, in 2018 and 2019, where we brought together Korean doctors and nurses and partnered them up with computer science students from universities there. And we're hoping to come back there at some point. And the success of these events is really reliant on the availability of data. In the past, we have brought the data sets that we have created, but increasingly we are convincing our partners to use local data sets so that the models are relevant to the population that they represent. Let's go to our topic today. 2021 marks the 10-year anniversary when computers were able to beat human contestants in the game show Jeopardy! This marks the start of the modern age of artificial intelligence. And the machine learning community set their eyes on healthcare, which in the United States is a $1 trillion industry that is beset with medical errors, with uncertainties. A decade later, we have fallen short of the promise that we have hyped about. IBM Watson Health, for example, a product that was meant to help doctors diagnose and treat cancer, ultimately failed. And they are now, IBM is now thinking of selling this product to another company. 2021 also marks the 5-year anniversary of Google DeepMind beating human champions in the board game Go. And just like IBM, Google DeepMind has seen some issues over the last few years. The biggest problem that we see in advancing machine learning, artificial intelligence, data science in the field of healthcare is the concern that using real-world data to develop algorithms will perpetuate any bias, any subjectivity, any disparities that are encoded in the data that is captured in the process of care. And the last thing that we want is to legitimize these biases and propagate them at scale. We discussed this concern in this piece in the American Journal of Bioethics. Right now, the key metric to evaluate algorithms is accuracy. That's the way we tell if an algorithm is good enough for launching. We see how well they predict, we see how well they classify. But just because an algorithm is accurate does not mean that it should be implemented. It is possible that an algorithm will only work for a certain segment of the population. And what it will do then is to widen health disparities. If that's the case, then we urge the developers and the implementers of the algorithms to stop, pause, and really understand how the algorithms are making the decisions that they are intended to deliver. So consider a bank loan algorithm. The ideal data set to build an algorithm to determine whether an applicant is able to repay that loan in the future would have everyone receiving the loan and everyone being given equal opportunity to pay that loan. But that data set does not exist. The data sets that we have now that are being used by machine learning experts to build these algorithms have excluded a large segment of the population deemed not to be able to repay that loan. And for that purpose, they were not even given a chance to prove that they're able to repay that loan. So what we are looking for is what we call a counterfactual data set. But those data sets do not exist. If we use real-world data to build algorithms to help banks to determine if someone will be able to repay that loan, then there is the risk that we will perpetuate the disparities that we see now, that the poor people will always going to be excluded from getting a loan, and we will not see any improvement in the world that we live in. In healthcare, the most common topic for machine learning is mortality prediction. Is the patient gonna survive or not? This by far is the largest chunk of machine learning papers that have been published in the medical literature. Last year, there was a scramble for similar scores or similar algorithms. As COVID started really ramaging through the world, professional societies and countries scrambled to find some objective score that can help clinicians to determine which patients are more likely to benefit to be admitted to the intensive care unit. So this is in a situation where you might have 20 patients who are sick and who are requiring ICU care, but you only have 10 beds. So how do you choose which ones to admit to the intensive care unit? And for that particular scenario, what we would like is an objective score that will tell us whether a patient is likely to survive the intensive care admission or not. If not, then the bed should be given to someone who is likely to benefit from ICU care. But we ask ourselves, are these scoring systems fair? Are they making fair decisions across different disciplines? And with that question, we went ahead and looked at several illness severity scoring systems that are in use primarily for research, because the different societies, the different public health sectors started looking at these illness severity scores for the purpose of triaging patients in the emergency room of whether they should go to the intensive care or not. We looked at 3 scores: Apache 4, OASIS, and SOFA. SOFA stands for Sequential Organ Failure Assessment Score, and by far it was the most common score that was adopted by different states last year in the US in order to triage patients as whether they are good candidates for admission to the intensive care. What we found is that all 3 scores over-predicted the probability of death across different race ethnicities. But the degree that it over-predicted the risk of death was so much more among minority patients. Here in the United States, the score is bound to over-predict death among Blacks and Hispanics compared to white patients. That is true for OASIS and Apache, and it was also true for SOFA. And as you could see here, the calibration of SOFA, as evidenced by the standardized mortality ratio, is so much worse for Blacks and Hispanics. So the doctors and the nurses might find solace when they're using these scores, thinking that these scores would be more objective than they are. But unfortunately, a lot of the scores that we use now in healthcare were designed around white patients and may not perform as well when we employ them in other types of patients. In Korea, race ethnicity may not be a factor, but I could assure you, every country that we go to, there are populations that are marginalized. There are populations whose outcomes are worse than the other patients, even though they have the same illness severity, even though they have the same chronic medical conditions. So when we build machine learning models, the assumption is that similar patients receive similar treatments, but that is not the case. As we show here in papers that were written by our group, patients might be similar, but they receive different quality of care, leading to different outcomes. In these 2 papers, what we showed is that the outcomes of patients admitted for sepsis in hospitals that disproportionately treat more minority patients tend to have worse outcomes. And these observations will now be encrypted when you build algorithms. What's going to happen is you're going to keep predicting bad outcomes for patients who don't receive optimal care now. And of course, there will be a self-fulfilling prophecy. And what happens is this becomes permanent when we are using these algorithms in the process of care. We also know that there is a lot of subjectivity in the way we make decisions. Women who develop heart attacks have better outcomes if they are cared for by women cardiologists. Their outcomes are worse if their heart specialists are male. We know that Black newborns here in the United States have better outcomes if their pediatricians are Black. So given all this subjectivity that occur in decision making, what we are concerned about is that this subjectivity would also be reflected by the algorithms when we use them. We have several examples of algorithms in healthcare that are biased. The most popular example was published by Ziad Obermeyer and company in Science in 2019. They were looking at an algorithm that is supposed to predict whether a patient will have a complicated course and will require more care in the future. And what they found is that Black patients were less likely to be flagged as someone who will have complicated care in the future. And for that reason, they were less likely to be referred to a complex care management team. And of course, that would lead to poorer care for these patients. Our colleagues at MIT and University of Toronto were looking at automated algorithms to read chest x-rays. And they noticed that these algorithms to automatically interpret chest x-rays were making more mistakes if the patient were Black. And this was very baffling to us because the model only uses images without clinical data, and to train them to see whether a chest x-ray would show pneumonia, pneumothorax, pleural effusion. So how come it was making more mistakes when the patient is Black compared to a white patient? And this was very troubling to us. So one of the hypotheses, which we thought was ridiculous, was perhaps computers can tell the race of a patient based on the chest x-ray alone. So we went ahead and see whether that is the case. And we were surprised that computers were trivially easy to train to identify race. This slide here shows the performance of algorithms that we trained to identify self-reported race in medical images. As you could see here, it was very easy for the computers to pick up. And we were wondering, how are the computers learning what the self-reported race is from the medical images? And we performed lots of experiments. Is it the disease distribution? Is it possible that Black patients are more likely to have pneumonia? And if the patient has pneumonia, then the computer will identify that chest x-ray as belonging to someone who is Black. But that wasn't the case. We looked at only patients with pneumonia, and still we were able to determine whether a patient is Black or white. Perhaps it was the age distribution. As you know, you could determine the age of a person from the bones in the chest x-ray. And it wasn't that either. We would look at chest x-rays belonging to the same age group, and every time the computers are still able to tell whether the patient is Black or white. And we replicated this in other types of medical images. We were able to see this in wrist x-rays. We were able to see this in neck x-rays. We were able to see this in CT scans of the chest. And a group in London was able to replicate this in MRIs of the brain. And we were completely stumped in terms of determining how the computer algorithms are able to do that. We even downgraded the quality of the images to a point where there's no discernible anatomic landmarks anymore. And every single time, it's still able to determine what is the race of the patient. And this is very troubling because if computers can tell sensitive attributes such as the race, it probably could tell sensitive attributes such as gender, such as certain demographics. And if they could do that, then it's not far-fetched to think that computers can also be biased, just like humans. After all, we're training the algorithms using data that capture the behavior of humans. So it follows that algorithms that you develop using real world human data are bound to be biased. And we've seen this in facial recognition software. We've seen this in algorithms that are used, for example, to filter curriculum vitae from applicants to a job or school. They are bound to reflect societal biases. And this is what we don't want to happen. Which brings me to the story of Clever Hans. Clever Hans is a horse, is a Arab stallion. And in the 1900s, he was bought by a schoolmaster called William von Austin. William von Austin decided to teach Clever Hans how to recognize numbers and how to perform calculations. And he was very excited when he learned that the horse can do simple arithmetic, such as additions and subtractions. And he would have road shows to demonstrate how smart Clever Hans was. But it turns out that the horse was not actually making subtractions and additions. The horse could detect the heartbeat of people around him. So every time the schoolmaster would point to the correct answer and the audience would get excited, Clever Hans would think that that's the right answer. When they made experiments where they did not tell William von Austin or the audience what the question is, Clever Hans was not clever at all. He was not able to give the correct answer. Are there examples of Clever Hans in machine learning? Absolutely. These are investigators from UC Irvine and University of Washington who decided to teach computers how to differentiate a wolf from a husky by feeding the computers photographs of wolves and photographs of huskies. But it turned out that all the photographs of wolves had snow in the background, and none of the photographs of huskies had snow. So very quickly, the computers learn to base their decision on whether there is snow in the background rather than learning that from the features of the animal. So this is a perfect example where the computers take cues from features in the input that has nothing to do with the classification or the prediction. And we're afraid that this is also going to be the case if the computers can learn sensitive attributes, whether the patient is Black, whether the patient is poor, whether the patient is morbidly obese, whether the patient is LGBTQ. And we're afraid that if that is the case, then we're doomed. We're not going to fix any of the disparities that we're seeing now. Given the high stakes of a wrong classification or prediction when we build machine learning models, we would think that we would like to represent the majority of the population in the data sets when we're building algorithms. But that is not happening. A paper that was published in JAMA last year found that in the United States, the vast majority of papers that showcase a machine learning algorithm would use data coming from only three states out of the 50 states. And those are California, New York, and Massachusetts. It seems that by race, gender, or geography, the machine learning community has a diversity problem in their data sets. And for that reason, we are not surprised when we're finding algorithms to be biased against certain fractions of the population. From a world perspective, this is also a big problem. Our group reviewed all the papers that were published in PubMed in 2019 that employed machine learning methodologies. And we found that 40% of papers use data sets coming from the United States, and the rest of the world is not well represented in the area of machine learning. As you can see here, there are only a few countries that are represented when it comes to machine learning in healthcare research. And we think that this is going to perpetuate and contribute to the very unequal map of the medical knowledge system, which for the last 100 years have informed the way we deliver care. As you know, the way we deliver care right now is informed by research that are performed in a few countries. The way we treat diabetes, the way we treat hypertension, the way we diagnose Alzheimer, we don't perform research in every country, in every continent. For the most part, most of the research will take place in the rich countries, and whatever findings that we arrived at in those research is translated into treatment recommendations that are followed in the rest of the world. With the digitalization of healthcare, there is now an opportunity to redraw the world's very unequal knowledge map. There is an opportunity for every country to build their own medical knowledge system and to be custodian and the contributor to their own research. And on this note, we introduce this concept of village mentoring and hive learning. This is a new method of teaching that we have adopted and we're trying to promote around the world. This pertains to bringing together people with different backgrounds, people with different experiences, people with different perspectives, and allowing them to address the questions, the uncertainties that we have in healthcare. So we call this hive learning because everyone is learning together, everyone is learning from each other. And the goal here is to take advantage of each other's perspectives, take advantage of each other's expertise. This is easier said than done. Everywhere in the world, people are doing research in their own silos. They're not leveraging the wealth of know-how, the wealth of skills that are available in their countries. So once again, I wanted to summarize my presentation. Machine learning and artificial intelligence are nothing but encoding the clinical practice that we have now, encoding the medical knowledge system. But the same clinical practice leads to disparities in care across populations. The medical knowledge system that we use in building these algorithms is primarily drawn from research in a handful of countries. And we think that this is not acceptable. Now we have an opportunity to include as many investigators as possible, bring them and allow them to contribute their expertise, their perspectives into providing a better recommendation and better suggestions on how to test and treat different diseases. And we could come up with recommendations that are specific to each country or even to each locality so that we understand health and disease better in a more precise way. And with that, I'm happy to answer any questions from the audience.
Dr. Leo, thank you very much for very excellent lecture and comprehensive information. Okay, we have a question from the audience. Okay. One question is, do you have a plan to restart worldwide data zone again? What are you planning on data zone?
Yes.
Yeah.
No, we have 15 datathons that are lined up for 2022 and 2023. So the plan is to go back to pre-COVID times. where we are hoping to break down the silos, separating the clinicians from the computer scientists in every country of the world. So we're hoping to be back in Korea at some point, maybe next year, maybe in 2023.
Okay. And we have another question also. One question from Dr. Hyungjun Kim from Aju University. His question is, thank you for your useful lecture. I have one question. Until now, no matter how accurate our AI is, it only assists human decision and has not been replaced. However, like the title of your lecture, it is clear that AI will make a much fairer judgment than humans. If AI is fairer and more accurate than humans, do you think it can replace human decision? It is very difficult question.
Yeah, so I don't think AI will replace humans ever. Perhaps in the very easy decisions, it can do that. But for the more complex cases, I think that AI is supposed to be partners in crime. I hope not crime, but partners of doctors and nurses. Like they are there to make sure that we are making objective decisions. My vision for AI is that it would alert us if we have some unconscious bias that is coloring the way we're making decisions. Like, for example, even when I work at 2 a.m. in the morning, my brain is not at 100%. And that's really the time when I want a computer to help me and make sure that I'm able to integrate all the data that is being captured for a certain patient who's suddenly deteriorating in front of my eyes. So I will deviate from what the other computer scientists have said in the past, like Jeff Hinton and Andrew Nang, who said that computers will replace doctors in the future. I don't think so. I think that doctors and nurses and pharmacists and other healthcare professionals are always going to be there, but their performance will be augmented. Their performance will be enhanced by allowing them to work with computers who are able to synthesize so much more data than the human brain can do.
Okay, thank you. Another question is Yoo-jung Kim from Yonsei University, and the question is, as I know, Mimic is one of the largest database for research. Do you have any plan to enlarge your database by collection real-time data between other U.S. hospitals?
Yes, so we already have the EICU Collaborative Research Database that has data from more than 200 hospitals across the United States. It currently contains 200,000 ICU admissions, and that has been available as well to the research community for the last 5 years. And there are more to come. I'm aware that there's also a Vitals DB from Seoul National University. This is data coming from patients who undergo surgery. So it's a perioperative database that is also available to the research community now. There are a number of ICU data that have been made publicly available from Europe. There's one coming from Amsterdam called Amsterdam UMC database. So it comes from Amsterdam University Medical Center. There's another database coming from Switzerland called Inselspital, which is a university hospital in Bern, Switzerland. That is also available through the FissionNet platform, which are group hosts. So I think that we are moving in the right direction, slowly but surely. We are working with a hospital in Brazil, a hospital in Chile, a hospital in Uganda, and they are all inspired by the Mimic experience. And they know that to fully leverage knowledge that is encrypted in these data sets, they have to be accessible to as many experts as possible. I think the model where only internal investigators can work with a data coming from a hospital is not efficient. It's not maximizing what we could learn from those data sets. And based on the Mimic experience, Mimic alone has produced tens and thousands of publications and conference proceedings. It is the most intently studied ICU cohort in the history of the world. Just imagine if we can do that with hospitals in Korea, whereby there will be thousands of publications coming out to study the electronic health records of patients in Korea. I think that this is the way to build a medical knowledge system that is Korea specific, and that should be the goal of the medical profession, of the nursing profession, is to build their own knowledge system so that they are not reliant on research performed in other countries.
Okay, thank you. You already answered the question, but the other Chanmin Park asked from Yonsei University asked question, and South Korea is also working on project to build an ICU database such as Mimic data. What are the most important things to consider, or any tips you would like to share? Maybe you answered the.
So I think the challenge that we see is that people are always they say that they are concerned about patient privacy, and for that reason they don't want to share the data. But what we could say is that if you de-identify the data set meticulously, it's virtually impossible to re-identify someone from a publicly available data set. We recently reviewed all papers and all news articles looking for specific persons who were re-identified from a publicly available data set. And in the last 20 years, there was only one. Consider this, compare that to the number of reports of hacking healthcare systems. To us, hacking of healthcare systems is a much bigger risk than the risk of re-identification in a de-identified data set. And the risk is not zero, we admit that, but the risk can be mitigated to a point that it is offset by the benefit and the value of sharing this data and allowing it to be analyzed by a large group of investigators. Most of the time, I mentioned earlier, people use patient privacy as an excuse not to share data. In reality, it's politics. In reality, it's principal investigators who don't want other investigators to publish off their data set. This by far is the biggest obstacle that we've seen. It's politics and economics. Economics because hospitals think that they could sell the data to companies, but in truth, having a lot of data is one thing, but curating the data is much more difficult. And you cannot perform machine learning on raw data. There has to be a lot of pre-processing, harmonizing, standardizing that need to take place. And that requires a lot of doctors and nurses performing this curation. And I could tell you that no company will be able to provide the curation that is needed before you can analyze the data. Mimic is successful. EICU collaborative research data is successful because we are crowdsourcing the curation. I mentioned earlier that there are repositories that we have made publicly available. These repositories contain materialized views so that researchers don't have to start from scratch. There are codes and queries already to identify patients who develop sepsis. There are codes and queries already for patients who develop acute kidney injury, so that people don't have to curate from scratch. So being able to crowdsource curation is the biggest contribution that we've provided to the research community. Commercial data sets are always, I'm always very suspicious of how they curate the data set. We're always afraid that there are biases that are introduced when they make their own assumptions, because you need hundreds of pairs of eyes of clinicians to see whether the curation is accurate or not. And companies who are doing this that would have one or two clinicians, I am very skeptical that they are making proper curation of the data set before they build models. And for that reason, we really fully advocate to adopt the mimic model, where meticulously identification is performed. And after that, this is shared to the research community.
Okay. We have a question from the floor, and please introduce yourself and question.
Thank you. Enrique Martins from Portugal. Thank you so much for your presentation, and just at least look at you. Some people say that it is possible to educate AI on ethics. I would be curious to know your opinion on those type of statements. Thank you.
Yeah, so one thing that we're doing is to try to see if AI could be more fair. And one thing that we are trying out is to see if we could fool computers. For example, going back to the bank loan algorithm, we know that the algorithm uses features pertaining to the applicant. And we also know that in a lot of the decisions, the most important feature is the zip code here in the United States. If you live in a zip code where majority of the people who live there are Blacks, the algorithm would usually predict that you won't be able to pay your loan. But what if you can fool the algorithm and switch the zip code of that person to another zip code, so that it forces the computer now to look at the other features? So without the zip code, perhaps it will come up with a more fair decision. So we call this like adversarial attacks on the data sets, adversarial clipping of some features. Can we use this to alert us if we're making a biased decision? Can we use this to alert us if we're making some prejudiced treatment decisions? And that is my vision for AI, is to be able to tell us where our decisions might not be optimal for a certain patient. I have this very memorable story that happened to me, where a patient was misdiagnosed just because the patient was Black and young. They thought that the patient overdosed when he presented unresponsive, and the diagnosis of sepsis was completely missed. Because, and I'm not blaming the doctors and the nurses. We are humans. We are gonna make those unconscious bias decisions. And perhaps that is the occasion where the computers would step up and say that, hey, are you treating this patient based on the color of his skin? Are you treating this patient based on his accent when he speaks? That would be an amazing contribution if we could develop those types of AI.
Leo, your topic is very interesting, and we have so many questions. This question is also very interesting. About the AI model that differentiated between Black people and white people, have we tried to looking at activation maps? I'm very curious about what the model was looking at to make the decisions.
Yes, so activation maps are not that helpful. So we've done like heat maps and saliency maps and activation maps, and it's not as straightforward. So our goal is, when we build neural networks, we're looking for the racist neurons. Can we identify a racist neuron and remove that? And if we remove that, can it still perform the task that it was designed to deliver without affecting accuracy? There was a recent paper that found that making algorithms more fair makes it less accurate. And to me, that's perfectly fine. We have to find a balance where do we prioritize accuracy when accuracy means that we're going to continue to have disparities, or do we prioritize fairness? And I think more and more the machine learning community is leaning towards fairer algorithms, even though they lose some accuracy in the process. But research in this field is at its nascency. I'm excited by this field of research. I think potentially this is a game changer in the field of medicine. Perhaps finally we're gonna move the needle in terms of reducing disparities in care, because to a certain extent we have failed as a society because we're seeing the same disparities as compared to 50 years ago. Despite the establishment of public health schools, we have not moved the needle. We have the same problems that we've seen in the last 50 years. And perhaps bringing in the mathematicians, the computer scientists, the engineers, in addition to social scientists, we will finally make some headway in terms of reducing inequities in health, in terms of addressing uncertainties, in terms of reducing medical errors. So I think this is a very exciting time to be in the healthcare sector. It's a very exciting time to be in the informatics field, in the field of computer science.
Okay. This question is from Deong Yoon from Yonsei University. And how can we overcome the inequality problem of AI-based production? What's your suggestion?
So we have a checklist, and unfortunately the checklist is not complete yet, but we come up with specific items that people have to follow before they even build an algorithm. So the first thing is that you need to know what disparities exist in the domain that you are planning to build an algorithm for. And you need to understand all the drivers of disparities. So as I said, in Korea, it may not be race, ethnicity, but it could be the socioeconomic status. It could be their other demographics. So we know that in every part of the world, there are certain populations that are marginalized by the healthcare sector. And who are those? Those are the alcoholics, the IV drug users, the morbidly obese. They tend not to get the best care. So you need to have an understanding of who are the people who are not getting optimal care in the domain that you're wanting to build an algorithm for. And the second is that when you look at the data set, you have to know how the patients got into your data set. So when we're working on an ICU data set, perhaps there are some people who die even before they get admitted to the ICU. And that creates a sampling selection bias because not everyone has equal opportunity to get into the ICU. And that leads to spurious associations to be discovered when you build your models and to be incorporated in your algorithms. And you have to be very careful. So again, we are always paranoid that the data set that we have is already biased when it comes to sampling selection. And then what the machine learning community pertains to when they talk about fairness metric is to make sure that the model performs consistently in terms of accuracy across the marginalized population. But I wanted to say upfront that just because the algorithm is accurate in the marginalized population does not mean that it's fair. Because as I said, if our ground truths for which we evaluate algorithms is the real world data, then there's something wrong there because the ground truth is not fair. So the missing part of our checklist is what do you do so that you don't perpetuate a ground truth that is not fair? And that's where I mentioned some of the experiments that we're performing, where we're doing some adversarial clipping, adversarial attacks on the data sets and the models. We want to fool the algorithm so that the algorithm is not going to be as biased as the humans that we created the data from. And finally, the most important thing is you monitor the algorithm after it is deployed. I'm very frustrated with a lot of industry here, a lot of hospital leadership, because they think algorithms are an end product. And we try to tell them that algorithms are not like drugs, they're not like medical device, where once you've developed them, you could just buy them and plug them into your system. Algorithms need to be constantly monitored, constantly recalibrated, because we know that it's going to perform less well over time. There's one thing that we call calibration drift, and that is very well documented. The accuracy would deteriorate over time. And more important than accuracy is to monitor the algorithm in terms of what is it doing when it comes to disparities in outcomes. If only the rich people are getting better outcomes, then you have to stop and recalibrate your algorithm, because what you're going to be doing is you're going to be widening the disparities, the inequities in healthcare. So these are the steps in the checklist that we created. There are still missing steps. We still don't know how to fix once you find that the ground truth is not fair. And we hopefully would recruit some brilliant minds in Korea to help us in this research topic.
Okay. Maybe this is the last question because we have only 4 minutes left. And this is Howard Lee from Seoul National University Hospital. Excellent lecture and thank you. What do you think is the biggest reason why IBM quit doing biz with the Watson for some things? By the way, we met last data zone a few years ago at Seoul National University Hospital, and it's great to see you.
Great to, well, I don't see you, but it'll be great to see you again next year or in 2023. I mean, we've read what the problems were with the IBM Watson Health. They trained the algorithm based on publications, looking at PubMed and other sources of studies and trials. And of course, those trials disproportionately enrolled people from academic institutions in the United States, such as Memorial Sloan Kettering, MD Anderson. And it was no surprise that the optimal treatment suggestions would not work for patients in India or patients in other parts of the world. And this is a good example of my favorite saying that the accuracy of a model is bound by space and time. So an algorithm that we develop using data from Beth Israel Deaconess Medical Center may not be accurate even when we apply it to the hospitals just across the street here in Boston at Brigham and Women's Hospital, because there are differences in practice patterns between Beth Israel and Brigham, which would change the relationship of the features and the outcome. So for the entrepreneurs out there, please don't follow a business model of, I want to build an algorithm and then I want to sell it to as many hospitals as I can. Because potentially you may be killing patients, you may be harming patients, because a model that was built in hospital A may be dangerous to a model that may be dangerous to hospital B. And I also said that the accuracy of the model is bound by time. So a model may work well at Beth Israel. A model built using data from Beth Israel may be performing well now at Beth Israel, but I could tell you in 2 years, it's not going to perform as well. So hospitals need a process by which they could monitor the performance of their models, not just in terms of accuracy, but performance in terms of their impact in health inequities. And there has to be a process to address calibration drift. There has to be a process for updating techniques.
Thank you, Dr. Leo. Thank you very much for your excellent lecture and full-time dedication for Q&A session. And I hope we will see you again in face-to-face, maybe next year.
Sounds good. You have a good day. Thanks very much.
Bye. Thank you very much. 네, 아주 닥터 레오의 좋은 강의를 듣고 여러 선생님들의 Q&A 세션을 잘 진행한 것 같습니다. 한 2분 정도 Q&A를 못 하셨는데 애석하게도 시간이 짧아가지고 2분의 Q&A는 오늘 못해서 좀 죄송하게 생각합니다. 이것으로 키노트 렉처를 마치겠습니다. 감사합니다.